right, sound check, sound check. Okay, I can hear myself there. Perfect. And we need to do a video check. Do I see my hand moving there? Give it a couple seconds. Yes, I do. Okay, perfect. Headphones can go away. And if you hear that music in the background, that is my neighbor. They decided to play loud music just like 10, 15 minutes ago. This isn't even a regular occurrence. I don't know what's going on, but we'll work with it. The show must go on. Okay, so I did adjust the video settings a little bit, hopefully, because I saw in the footage of the last part that this corner was a little bit too bright and hard to read, but I think I've lowered it enough to where now everything is readable, so we should be good. And yeah, I should probably go out and buy another light source or two just to get the lighting perfect. I think that's gonna be the trick. Multiple light sources is probably gonna be the fix we need in order to get this just perfect. But I mean, this is good enough. We can work with this. Anyway, where do we want to start today? So for today, the plan is just to wrap up the Force chapter. I know some of you have been ready to wrap it up for a while, but there's a reason why I insisted on covering this topic so extensively. I've said it before and I'll say it again. Force is what I consider to be the most important chapter in all of physics. Once you master the concept of force, you develop this thinking style, I believe, that gets you through everything else in physics. But yeah, today we're going to wrap up with some of the toughest questions I have in these books of mine. And next time we will start energy, which might actually be in a couple days. We might not have to wait all the way until Sunday, but I'll do the usual. I'll schedule the next one for Sunday, but move it up if I have the opportunity to do something sooner. And I'm going to say up front, no time for traditional office hours so far. Maybe I can do one on Monday. We will see, not making any promises. Okay, so Force chapter, let's just get straight to whatever it is that needs doing today. So last time I left you guys off with this question. Let me find it. So it said, a sled weighing 60 newtons is pulled horizontally across snow so that the coefficient of kinetic friction between sled and snow is 0.1. Coefficient of kinetic friction between sled and snow is 0.1. A penguin weighing 70 newtons rides on the sled, as in the figure, and if the coefficient of static friction between penguin and sled is 0.7, find the maximum horizontal force that can be exerted on the sled before the penguin begins to slide off. So there's a force being applied directly to the sled. The penguin is dragged by friction force up to a certain point where the penguin will start to slip. And we need to figure out what is the maximum applied force before that slipping begins. So an object is about to slip when the static friction that's supposed to prevent it from slipping is maxed out. Because at that point, you just apply a little bit more force and the friction can no longer catch up to it. And so the object, or in this case, animal, begins to move relative to the surface that they are in contact with. So that is our goal. Not really super hard. We've done enough problems at this point that this shouldn't be too much trouble for us. It's really just a matter of getting the diagrams right. We have two objects, so we need two diagrams. So object 1 is going to be our penguin. Object 2 is going to be our sled. I'm just going to draw a horizontal block to represent the sled so that I don't have to spend too much time drawing. Okay. For the penguin, we have force of gravity, of course. Force of gravity penguin is what I called it. And that's 70 newtons. We've got a normal force between the penguin and sled. I'm just going to call it, what should I call it? I guess I'll call it normal force sled. It's the normal force between the sled and penguin. So normal force, I'll just call it normal force sled for short. We don't have, the applied force is not directly on the penguin, but if static friction is acting on this penguin, then it will act in such a way as to oppose the direction of attempted motion. If the sled is trying to move to the right relative to the penguin, then it's as if the penguin is trying to move left relative to the sled. So static friction opposes that leftward relative motion, which means static friction would have to be to the right. Force, friction, static to the right. And that is it for the diagram of the penguin. Now for the sled. For the sled, we've got force of gravity, of course. Force of gravity, sled. We have a downward normal force between the penguin and sled. It's just going to be the reaction to this force over here. So that's going to be what we call normal force sled. Upward, there's a normal force from the ground. I guess we'll call it snow. Normal force snow. There is, since the sled attempts to move right relative to the penguin, if the penguin was slipping, the sled would be moving right relative to it, so the static friction must be opposing that, so the static friction must be to the left. You can also reason that it's just the reaction to the static friction on the penguin. If the sled were to slip due to being pulled like this, then it would be as if it's moving right relative to the penguin, and relative to the ground as well, but more importantly is the direction of its motion relative to the penguin. Since it's also moving right relative to the ground, the friction between it and the ground would be to the left, so there's going to be a force of friction kinetic, force, friction, kinetic between sled and snow that acts on the left for the sled. If I were to draw a diagram of the snow itself, then the reaction to that kinetic friction force would be pointing to the right, but of course we're not concerned with the motion of the ground, so no need to draw a third diagram for that. Let me think. Am I missing anything else? Oh, of course, the star of the show. Force applied. That was mentioned in the problem. Okay, now with our diagrams complete, let's see what we can write in terms of our equations. What kinds of equations do we have here? So for the penguin, net force vertical is going to be 0. Net force y, I'll just call it P for penguin is equal to forces up minus forces down. So, well, first of all, is equal to 0 because we expect no vertical acceleration for the penguin, and is equal to forces up minus forces down. I will define up as the positive direction, just what we usually do in other words. And we know force of gravity penguin is 70, so normal force minus 70 equals 0. Therefore, we can conclude that normal force that the sled exerts on the penguin is equal to 70 newtons. Okay, and then net force in the x direction on the penguin is, well, just the static friction force. So it's going to be the mass of the penguin times whatever the acceleration is. If it's before the penguin slips, then it should be accelerating at the exact same rate as the sled underneath it, so that their motion relative to each other is 0. So I'm just going to call that a system. And that's going to be equal to just force of friction static. And if it's about to slip, then that's going to be equal to its maximum value equals mu static of the sled maximum, as I called it. Why did I give them such long names? Times the normal force between penguin and sled. Times normal force between penguin and sled. So actually we can go ahead and calculate this. So for the mass of the penguin, we know the force of gravity on the penguin is 70, so the mass of the penguin must be 70 divided by g, right? If mg is equal to 70, then divide 70 by g and you get m. So 70 over 9.8, a system, equals mu static maximum is 0.7 times the normal force between penguin and sled is 70. So that's gonna be 49. And then 49 times 9.8 divided... Oh, wait a minute. Actually, I can do better than that. I can cancel the 70s and just do 0.7 times 9.8. Oh. 0.7 times 9.8. Whoops. Syntax error. What did I... Oh, accidentally pressed the negative sign for some reason. 6.86. So the acceleration of the system is 6.86 meters per second squared. Interesting. Now to figure out the sled. The sled has a lot more terms in it, so other than that, there shouldn't be much difficulty. It's just the number of terms is a bit overwhelming. Okay, so net force in the y direction, net force y on the sled is going to be 0, of course. We don't expect this sled to accelerate up or down. That's just our common sense. And that means that the normal force that the snow exerts on the sled upwards minus these two downward forces, normal force sled and gravitational force sled should be 0. A normal force that the sled exerts on the penguin and that the penguin in turn exerts back on the sled is 70 newtons in magnitude. Force of gravity on the sled we were given is 60, so we've got minus 70 and minus 60. Normal force snow minus 70 and minus 60, so minus 130. Normal force snow minus 130 equals 0, therefore normal force snow, therefore normal force between sled and snow is equal to 130 newtons, the combined weight of both penguin and sled. All right, and we can use that for our friction forces. So let's go ahead and write net force horizontal on the sled. That's going to be the mass of the sled times the acceleration of the system equals forces right minus forces left, force applied, minus force of friction kinetic and force of friction static. So minus force of friction kinetic and minus force of friction static maximum. Did we actually calculate this? No, we didn't. We canceled the 70 in it, but 0.7 times 70 is what it would be, which is 49. So force applied minus mu kinetic was 0.1 times normal force snow was 130, so that will be the kinetic friction, and then minus, we said the static friction when it's maxed out is 49 newtons. And we can get the mass of the sled by simply taking the force of gravity on the sled and dividing by 9.8, and we know the acceleration of the system is 6.86, so we should be able to do this just fine. Mass of the sled is going to be 60 newtons over 9.8 times the acceleration of the system is 6.86 equals force applied minus all this equals force applied minus 0.1 times 130 is 13, so minus 13 and minus 49, or minus 12 and minus 50 in other words, so minus 62. Okay, and add 62 to both sides and we should have everything, so 60 times 6.86 divided by 9.8 is equal to 42, and add 62 to that, and that gets me exactly 104. Force applied equals exactly 104 newtons. Any more than that, and the net force on the sled will be high enough that it accelerates faster than the penguin does, and the penguin will start to fall back and eventually just fall off the sled. Now, one thing I didn't do here is I could have, instead of plugging in numbers here, I could have just carried on, and I think we wouldn't have had to find the exact masses of the penguin and sled if we did that, because I think all of those 9.8s that we divided by would have canceled out. I mean, we can take a look real quick. No harm in taking a quick look. So let's see. I could have kept this as if I took just both of the horizontal equations and put them together, the force of static friction maximum would cancel out if I were to add this equation to this one, and I would get m sled plus m penguin all times the acceleration of the system equals force applied minus the kinetic friction force on the sled and then this would be mu times, let's see, that would be force applied minus mu kinetic of the snow times the normal force that the snow exerts on the sled is just going to be m sled plus m penguin all times g. And if I add that over to the left-hand side, well, actually before adding that to the left-hand side, I can say the acceleration of the system over here, if I were to rearrange this, is just multiply the g over to there. Okay, hold on. Let me rewrite this. So m penguin times acceleration of the system is equal to, I'm just going to call it mu static for brevity's sake, times the normal force would have been m penguin times g. So yeah, mass of the penguin cancels out and it's just mu static times g for the acceleration of the system. Okay, yeah, and then so it's going to be m sled plus m penguin times mu static times g equals force applied minus, I'm going to rearrange this, move the mu over to the right and have m sled plus m penguin again times mu kinetic times g, and then if I add this to the left hand side, then what do I get? Well, I would still have the m sled plus m penguin, I'll just call it big M, the total mass, times the g, and then times mu static plus mu kinetic. I would get force applied equals big M times g times mu static plus big M times g times mu kinetic. In other words, big M times g times mu static plus mu kinetic. And big M times G is just going to be the sum of the two weights, 60 plus 70. So yeah, you never actually had to calculate the masses of the penguin or sled in kilograms, you could have gotten away with just continuing to use the 60 and 70 throughout the whole problem. So, yeah, that's the cleanest answer we have. So if this was given to you as a free response question on the AP exam, and you were told, derive an expression for the applied force in terms of the given information, you wouldn't even write big mg. You would write, instead of the big mg, you would write W sled plus W penguin, or force of gravity sled plus force of gravity penguin, whatever they want to call the weight. Sometimes they use W and sometimes they use FG. But yeah, that is definitely something that they could ask you. They could ask you to derive an expression like this. So another way of writing it would be force applied equals, and then they could say something like W sled plus W penguin. That replaces your big mg times mu static plus mu kinetic. Okay, let's look for another problem. I already know a couple of the ones I want and I have them in mind, but it doesn't hurt to read through some of the other ones and see if there's anything extra that I can add to the list. This one, I don't remember it being too easy, but I also am not sure how hard it is, so let me give it a read. It says a magician pulls a tablecloth from under a 200-gram mug located 30 centimeters from the edge of the cloth. The cloth exerts a friction force of 0.1 newtons on the mug and is pulled with a constant acceleration of 3 meters per second squared. How far does the mug move relative to the horizontal tabletop before the cloth is completely out from under it? Note that the cloth must move more than 30 centimeters relative to the tabletop during the process. That music is going to keep distracting me, isn't it? Of all the times I could have chosen to stream. Of all the times. Me and my luck. Anyway, let's do this one. It's got some kinematics in it, which is nice. Okay, backside of this isn't used yet, so let's go ahead and do that. So we have a 200-gram mug, in other words, 0.2 kilograms. So we have a mug. And it is under a piece of cloth, or over a piece of cloth, rather. And then that piece of cloth sits over a table. So we have a table here. And I guess we can add legs to this table. There we go. And the magician does that one trick where they pull the cloth quickly from under the mug and make it look as if, they pull it in such a way that the mug doesn't really get dragged that far. As if trying to create the illusion that the mug was simply floating over the table or something like that. I'm not sure what the purpose of that trick is, but any magicians out there watching, I guess you can let me know. I don't know if any magicians would be watching this, but, well, I mean, depending on the kinds of magic tricks you would want to do, I suppose a knowledge of physics is something that might be worth pursuing for some of you, but anyway. Information. So, mass of the mug is 0.2 kilograms, 200 grams, or 0.2 kilograms. And the mug is located 30 centimeters from the edge of the cloth, so we've got about 30 centimeters worth of cloth, depending on how you want to draw it. I would just draw it here like that. You've got 30 centimeters worth of cloth that needs to be pulled, I'm assuming, to the right from underneath this mug. I'm going to use right as my positive direction. So you've got 30 centimeters worth of cloth, or 0.3 meters in other words. And let's see. The cloth exerts a friction force of 0.1 newtons. So force of friction, and I guess this would be kinetic friction, force friction kinetic is equal to 0.1 newtons. And the cloth, the acceleration of the cloth, is 3 meters per second squared. How far does the mug move relative to the horizontal tabletop before the cloth is completely out from under it? Note that the cloth must move more than 30 centimeters relative to the tabletop during the process. How far does the mug move relative to the horizontal tabletop before the cloth is completely out from under it? Okay, so not actually too bad. We can immediately calculate the acceleration of the mug. So the mug is just going to have normal force upward and force of gravity downward, which cancel each other out. And then friction force is what's going to pull it to the right. And that friction force was already given to us. So we don't even really need to do anything here other than just force of friction, kinetic, on the mug is our net force, is equal to our mass times the acceleration of the mug. So 0.1 is equal to 0.2 kilograms times acceleration mug. 0.1 over 0.2 is 1/2, or 0.5, so acceleration of the mug is 0.5 meters per second squared. As expected, the acceleration of the mug is lower than the acceleration of the cloth. That's necessary for this trick to work. Also, because it's significantly lower, the faster you do this, the less time there is for the mug to move, which means it won't move very far, which creates the illusion that the mug didn't get pulled at all, but of course the mug does get scooted over just a little bit, and that's what we're trying to calculate. So the mug eventually ends up It has some acceleration to the right for some amount of time. We'll call that delta x mug. And the cloth has to move from, the edge of the cloth has to move from here all the way to this point in order to completely come out from under the mug. So that's delta x cloth. And the rest is really just a kinematics problem from here. So let's see what there is to see. Let me put the book over there and give myself some space here. So both cloth and mug start from rest. So I know V mug initial equals V cloth initial equals 0. We know the accelerations of both, and we don't know their displacements, but we do have a relationship between their displacements. And we also have a relationship between their times. The time that the cloth is in motion from this point to this point is also the same amount of time that the mug spends moving from this point to this point. At least this right end of the mug is moving from here to here. So if we go ahead and say T mug equals T cloth equals T, there we go. Basically just one stopwatch for the whole thing. And delta X cloth equals, let's see, it's going to equal delta X mug plus 0.3. It's going to equal delta X mug plus 0.3, as we can infer from our diagram. The 0.3, of course, is the 30 centimeters converted to meters. Okay, and we can use second equation of kinematics to replace these delta x's and rewrite them in terms of t. So delta x cloth is going to be v cloth initial times t. So 0 times t plus 1/2 acceleration cloth times t squared. That's delta x cloth. Equals delta x mug is also 0. V mug initial is 0 times t plus 1/2 acceleration mug times t squared. And then, of course, plus the 0.3. So the zeros, of course, don't do anything. 1/2 acceleration cloth, that's 1/2 of 3, so 1.5 t squared equals 1/2 of 0.5 is 0.25 t squared plus 0.3, subtract 0.25 t squared on both sides. 1.5 minus 0.25 is 1.25 t squared equals 0.3. Divide by 1.25 and let's see what we get. 0.3 divided by 1.25 is 0.24 on the dot, and that's t squared. If I take the square root, positive square root, because negative time doesn't make sense here, I'm getting 0.4898979949, or as I will round it, 0.490. So I'm getting t equals square root of 0.24, which equals about 0.4 0.90 seconds. Just under half a second. And then the actual question was, how far did it go? Right, so I circled the wrong thing. I'm just in the habit of circling any major conclusions. How far did the mug travel, or how far did the cloth travel? I mean, we can find out both, but how far does the mug move relative to the horizontal tabletop? Yeah. So delta x mug, that would just be the 0 plus 1/2 a mug t squared. So delta x mug equals 0 plus 1/2 0.5 times t squared is 0.24. Okay, so 0.25 times 0.24, 0.06. Hold on, 0.25 times 0.24. Yeah, 0.06 equals 0.06 meters, or 6 centimeters, which is actually noticeable. 6 centimeters is noticeable because it would be, I mean, if you started with 30 centimeters worth of cloth under 30 centimeters worth of cloth that needed to be pulled out from under the mug, then yeah, 6 centimeters relative to 30, that's 1/5. That's something you could detect by the naked eye. It's not very subtle, so I think this magician needs to practice their craft a little bit more. At least if their goal is to make it look as if the mug didn't move at all. But that is it for that problem. Here we go. One of the big problems that I definitely wanted to cover today. So it says, an inventive child wants to reach an apple in a tree without climbing the tree. Sitting in a chair connected to a rope that passes over a frictionless pulley, as shown in their figure, which I will draw in a minute, the child pulls on the loose end of the rope with such a force that the spring scale reads 250 newtons. The child's true weight is 320 newtons, and the chair weighs 160 newtons, and it wants us to show that the acceleration of the system is upward, and find its magnitude, and also find the force the child exerts on the chair. So, a lot to discuss here. But first, let's draw that diagram that they have. So, they have a rope connected to a spring scale, and then it runs over a pulley. And then it's holding a chair. So that's like the seat. And then on this seat, I'm going to use a different color for them. On this seat, we have a child sitting. And I guess I'm going to have to exaggerate this, but yeah, pardon the ridiculously long hands on this kid, but they are holding this rope and pulling on it in order to lift themselves up So yeah, they've got this pulley is hanging from the limb of a tree, and they're just tugging on this rope to pull themselves up. Let's read the problem again. An inventive child wants to reach an apple in a tree without climbing the tree. Sitting in a chair connected to a rope that passes over a frictionless pulley, the child pulls on the loose end of the rope with such a force that the spring scale reads 250 newtons. So this spring scale reads 250 newtons. And we'll talk about what that means in a minute, in case it's your first time seeing a rope connected to a spring scale. The child's true weight is 320 newtons, so force of gravity child is 320 newtons. And the chair weighs 160 newtons. Force of gravity chair equals 160 newtons. Show that the acceleration of the system is upward and find its magnitude. Find the force the child exerts on the chair. So we need to show that the acceleration is upward for the system being the child and chair, and find its magnitude. So what is the acceleration of the system? And also we need to find part B, the force that the child exerts on the chair, which is also the force that the chair exerts on the child. It's the normal force. Find normal force, and that's the only normal force that's going to be in our diagrams, so I'm not going to add anything else to its subscript. Normal force is good enough. Those are the two things we need to find. Okay, so what is the purpose of this spring scale? So let me actually pull out my spring scale so we can talk about this. Where did I put you? There you are. Okay, so spring scale. You've seen this thing before, at least if you've been watching previous episodes. If this is your first time watching this series, then welcome, and you probably want to go back and start from the beginning, because everything I cover builds on top of each other. Anyway, so spring scale. I pull on it, and of course depending on how strongly I pull on it, the spring stretches to greater distances, and of course if I stretch it double the distance, then that means that I applied double the force, and so on and so forth. And it is measuring not only the amount of force that I apply to it, but also the amount of force that it is applying to me in order to keep itself still, right? If I pull on it, I guess from your perspective, this would be down. If I pull down on this thing, it has to pull up to such an extent that it exactly balances out the force I'm exerting downward, so that the net force on it is zero, so that it's not constantly, swinging up or down. If I were to, remove my finger, then of course, for a fraction of a second, the net force on it is going to be upward, since there's nothing pulling it down anymore, and it accelerates, and it eventually hits whatever you want to call the inner casing, and then that exerts enough normal force to bring it to a stop and prevents it from accelerating up any further. So when I apply this force downward on the spring, it applies a force upward on my hand, but it's actually applying two forces. It's actually also pulling on both ends of the spring. So if I were to draw this, I guess we'll draw it over here. If I were to pull down on it, then it will pull up on me on one side, but it's also pulling down on the opposite side with an equal amount of force. It's also pulling down on the opposite side. And I know this because if I were to just pull it down, look what happens. I need to apply a force upward. I need to hold it over here at the top in order for it to stay still. If I don't have my other hand here holding it, then that's what happens. Every time I try to pull it down, the whole thing comes down. And notice when the whole thing comes down, how far does this go? I want to try and keep it from tilting over, but notice what happens. It doesn't go very far. The little white indicator thing, it doesn't pull down very much. In fact, if I do it fast enough, it barely does it at all. You might have to actually slow down the video in order to see it in action. Let's see. Hold on. Let's rotate that a little bit so that it's not hooking onto stuff. And let's try that one more time. So, yeah, you saw it barely budged. It barely registered any force. There was just a little bit when it started moving, and then it quickly went down to zero. This is kind of what happens in an elevator, where if you were to bring a bathroom scale to an elevator and stand on it, you would notice at first, when the elevator doors first close, it's just reading your weight. But then when the elevator begins to accelerate up or down, you notice a quick shift, and once the elevator picks up whatever speed it needs, it goes back to reading your normal weight, and then when it slows down to stop at the floor that you were meant to arrive at, you notice the scale reading shifts for a little bit again. That's kind of what's happening here. It's just a very quick shift. A very quick shift before it goes back to zero, because if the spring is moving with whatever's connected to it at a constant speed, well, then there is no acceleration, so there shouldn't be any net force. There shouldn't be any net force on it, so it just goes back to reading zero. So my point here is that springs not only read the force that exerted on one of their ends, they actually read the force that's exerted on both of their ends, and that force needs to be equal on both ends. That force needs to be equal on both ends. We normally don't think about this other end that's held in place because it's usually attached to something like a wall or a ceiling or sometimes even the ground, and we don't concern ourselves with the diagrams of the walls or ceilings or the ground or tables or whatever. But it is there. So we can talk about this some more later. I actually have another problem that we might want to discuss. Actually, do I have the page where I had my notes for that problem? It might be over there. I'll look for it later. But for now, what we want to take away from all that is this 250 Newton reading from the spring scale is basically measuring the amount of tension on both sides of that spring scale. It's telling us the tension in the rope. There's 250 newtons of tension pulling upward on one side of the spring, and there's another 250 newtons worth of tension pulling downward on the opposite side of the spring. That is not a very good looking 250, but I think you get the idea. Okay, so if there's 250 newtons pulling down on the bottom side of the spring scale, then there must be 250 newtons of tension pulling up on, well, this person. this person is pulling down on the spring, on this bottom side of the spring with 250 newtons. So the reaction to that must be 250 newtons acting up on them. So let's actually go ahead and draw the force diagram of the child and chair. So force diagram of the child and force diagram of the chair. For the child, we've got, since they pull down on the spring scale with 250 newtons of force, that rope must be pulling up on them with 250 newtons of force. You could call this the tension force or the spring force. It doesn't really matter as long as you correctly indicate that this is 250 newtons of force acting upward on them, on their hands. So there's 250 newtons acting up on them there. They're also going to have, I guess, the normal force from the chair acting upward on them. So normal force chair, or just normal force, right? We didn't have to specify here because it's the only normal force in the problem. And they've got, of course, their weight, which is 320 newtons F(g) child, which equals 320 newtons. Okay, so that is the child. What about the chair? So the chair, of course, has its weight downward, force of gravity, chair, which equals 160 newtons. And also, it's got the normal force from the child exerted downward on it. And it also has the tension force of the rope pulling up on it. There's also force of tension pulling up on it. And what is that tension force? Well, if the spring scale pulls down on its top end with 250 newtons of force, then the tension pulling up on it at the top end must be 250 newtons. And since the pulley is light and frictionless, we can assume that the tension on both sides is approximately equal. So there must be 250 newtons of tension in this side of the rope. So force of tension here is equal to 250 newtons. Okay, so now we can go ahead and write some equations. We only have vertical forces in this problem, thankfully. That's the one saving grace of this problem. And let's see, net force child is going to be m child times the acceleration is going to equal normal force upward plus 250 minus 320. Net force on the chair, net force on the chair is going to be m chair times the acceleration of the system equals forces upward, so 250 newtons of tension, minus forces downward, so minus the normal force, and also minus the 160 newtons of gravitational force. If we put these equations together, then we get m child plus m chair, m child plus m chair times acceleration of the system equals normal force and minus normal force cancel out. We get 250 plus 250 is 500. And then minus 320 and minus 160. 250 and 250 is 500. Minus, that's going to be 480. So we've got 20 newtons of net force, which is greater than 0. So at least we have some acceleration. Equals the acceleration of the system times, I'm just going to call it big M for the combined mass of child and chair. Big M, so that's going to be weight of child plus weight of chair divided by G. So 480 divided by G is what that is. So 480 over G, a system, equals 20. 20G equals 480 divided by 480. So 20G over 480. 20 times 9.8 is 196. Divided by 480 is 0.408. And then a bunch of repeating threes. I'll just round it to 0.4083. So acceleration of the system is 0.4083 meters per second squared. Okay, that solves the first part. Now to calculate the normal force, it's not going to be that much, it doesn't look like, considering how low the acceleration is. But yeah, all we have to do is plug it into either one of our equations. Let's use the first one, and let me change colors here. Let's do green. So we've got M child, which is going to be 320 over G, times the acceleration of the system is, I guess I can keep it written as 20G over 480. Yeah, I think that's what I want to do, 20G over 480, right? 20 times G divided by 480 equals a system. So yeah, 20G over 480 for the acceleration equals normal force, and then plus 250 minus 320, that's minus 70. So these G's cancel out, and 320 over 480 is 2/3, actually. 2/3 times 20, so 40/3 plus 70. So 40 divided by 3, and then plus 70 is 83.333. Normal force equals about 83.33 newtons. And there we go. Oh, and circle the acceleration because that was also one of the answers it asked for. Circle, box, whatever you prefer. All right, there we go. So now let me see if I still have it among my papers. Okay, I think this is the one. My work on this thing is a bit messy, but let us go ahead and look a little deeper into this spring inserted in between segments of a rope question. Let's go ahead and look at it. It makes for a nice expression problem. So, colors, let's use you. So the scenario looks like this. There are two scenarios actually. One scenario is you have a table with two pulleys like so. And then right here in this middle segment, there is a spring scale. There is a spring scale. I guess this is how I'm going to represent a spring scale. And the question says, you know, if you've got two masses here, and they're two equal masses, then what is the reading on the spring scale in terms of the masses of these blocks? And this can create a bit of controversy because some people will say, well, if the system is sitting still, as it should be if these two masses are equal, then that would mean that the force of tension in each segment of the rope, so whatever this mass is, it'll have a force of gravity, Fg, and then it'll have a tension force that's equal to that. And then over here, same thing, force of gravity must cancel out with the tension force so that the net force on each block is 0 so that the system doesn't accelerate. But then that would mean that there's a force of tension here, and there's a force of tension here. So what people argue about is, what will the spring scale read? Will the magnitude on the spring scale read 1 Ft or 2 Ft? And we already talked about why it's just going to be 1 Ft. Because this spring, if I stretch it to a point where it's exerting, let's see, how about 1.25 newtons, for example, over here? If I stretch it to the point of exerting 1.25 newtons, it's not just exerting 1.25 newtons that's split in half between both sides. I guess I should actually use something like 1 instead. Yeah, if I stretch it to 1, this doesn't mean that it's subject to a force of 1/2 on the right side and 1/2 on the left side, if I hold it like this. It is exerting 1 newton on the right and 1 newton on the left. It's countering both forces. My left hand over here isn't the only hand that's pulling on this. In fact, if I just hold my left hand still and come in with my right hand second and pull it to, can't rate it, 1 newton, now there's no room for arguing that my right hand has to be pulling on it too. Both sides are being subjected to a force. I know I've already talked about this, but bears repeating. And the spring force is exerting two forces, one on each end, to counter both of them in order to hold itself still. Or if it was moving with some sort of acceleration, then, you know, it could be something in between those two forces. So if you're still confused about this, there's a really good video on this specific question by, what was the name of the channel? Integral Physics. Integral Physics, all capital letters. They have a blue logo, I think, for their channel profile picture. I'll link it in the description or a comment or something later. But he has a video that goes over this and discusses it some more. My question is this: what if So if the masses are equal, then of course the conclusion is that the spring scale will just read whatever tension is actually in the rope, just one tension force, not 2 times that tension force. But what if the masses are unequal? What if one of the masses is smaller than the other? I'm going to call this one little m, and I'm going to call this one big M. Now, what is the reading on this thing? I guess this would be force of tension big M, and this would be force of tension little m. Well, actually, wait, no. No, it would be the same force of tension throughout, so no need to distinguish between the two. Don't mind what I was about to do there. I was about to screw it up. Okay, so now what is the force of tension and therefore the reading of this spring? Is it going to be just halfway between the weights of the two? Because if they were equal, if the masses were equal, then we already said that spring scale is just going to read a force of tension that's equal to mg. But now that we have two different m's, do we just split the difference and average them out? No. But there is a formula. There is a formula for a tension force in this situation that we can derive. It's probably not a very useful formula, because what are the odds of encountering this specific situation on numerous occasions? It doesn't occur frequently enough for this formula to see a lot of usage, but the point of the exercise is the derivation process. That's going to be the value in this. So can we get a general formula for the tension force and, by extension, the reading in that spring scale in terms of these masses, whatever those two masses may be? We can just solve it like a traditional pulley problem. So we can define a direction of positive motion, which I guess is going to be clockwise for both pulleys. And we can go ahead and write, I guess I'm going to call it net force big M is going to be big M times the acceleration of the system equals big mg for force of gravity minus force of tension upward, whatever that tension force may be, and then do similar for the smaller object, so net force little m. If you prefer L and S for large and small, that works too, in case your big M and little m look too similar and you fear that you might confuse yourself. But anyway, mass times acceleration of system equals, this time positive direction is up for the little block, so force of tension is positive while little mg is negative. And of course we can do the usual thing, add these two equations together, and we get mass times acceleration of the system. Oh, big M plus little m. I guess I'll write the little m first since I screwed it up. But little m plus big M times a system equals, the tension force cancels out, and we get big mg minus little mg. So big M minus little m all times g. And if I solve this for the acceleration of the system, then I get m minus big M minus little m over big M plus little m all times g. Okay, so that's a general formula for the acceleration of the system in this kind of scenario, but the question was to calculate the tension force. So now we have to take this and plug it into either of these. No matter which one you choose, you're going to get the same result. I will just choose, I'll choose the bottom one since it has force of tension already nearly isolated. Let's do this purple one. So if I choose the second equation, we have little m times the acceleration is big M minus little m over big M plus little m all times g equals force of tension minus little m times g. Okay, if I add little mg to both sides, then we get little m, that whole expression, minus, and then plus. I mean, we could just go with this, but I would like to simplify it even further. So let's see, what can I do? I could either factor out little mg and then do some hocus pocus with that, or maybe I should distribute. I think I'm going to factor out the little mg first. So factor out little mg, and then that's going to be times this plus 1. So big M minus M over big M plus 1 equals the tension force. And the 1 can be written as big M plus little m over big M plus little m. So that's going to be little mg times, copy that, and then the 1 becomes, I'll write it like this so that I can actually add those two fractions together. Okay, big M minus little m plus big M plus little m, the minus little m and plus little m will cancel out. Let's switch colors for this. So U will cancel with that. And that leaves us with 2 big M. So force of tension equals, we're going to have 2 big M over big M plus little m, and then times the mg on the outside. And now I can put that whole thing together and we can get 2 big M little m over big M plus little m, and then times G is equal to the tension force. Okay, so that's a general formula for the tension force in a simple situation like this where the rope doesn't snap and the pulleys are light and frictionless and all of our usual assumptions. That will give us the reading of the spring scale. So the mistake that some students will jump to, as I mentioned earlier, is that they might assume that they can just take big mg over here plus little mg over here and divide it by 2, and that will be the reading on the spring scale, which of course is not going to be the case. But let's ask the question, under what circumstances would that be the case? When? When, not when. That's bad. When is force of tension equal to big mg plus little mg divided by 2? When? Under what circumstances would that happen? Well, let's set the force of tension equal to this and see if some sort of relationship emerges between big M and little m. How must big M and little m relate to each other? What ratio must they have to each other in order for this to work? If force of tension equals big mg plus little mg over 2, then that would mean, I'll factor out the g and the 2, then big M plus little m times g over 2 must also equal 2 big M little m over big M plus little m times g. The g's cancel out. And let's see, I can multiply the 2 over to the right and multiply the m plus m over to the left, and that gets us big M plus little m squared equals, I multiplied the 2 over, so that should be 4 big M little m. If I FOIL this, then I get big M squared plus 2 big M little m plus little m squared equals 4 big M little m. This is a pattern that you might see a couple times here and there in your math class. If you subtract 4 big M little m, then what you get is big M squared minus 2 big M little m plus m squared equals 0. And considering that this over here, the big M squared plus 2mm plus m squared, considering that this is what we got from foiling big M plus little m squared, I think you might be able to see what this condenses into. This condenses into big M minus little m squared. And this leaves us with the conclusion that since big M minus little m squared must be 0, then square root both sides, square root of 0 is still 0. This would imply then that big M minus little m has to be 0. So the only time that the tension force is the average of the weights of the two blocks on either side is when the two blocks have the same mass. Otherwise, the tension force is never the average of the weights. And there you go. So that gives you, if you're presented with a problem that has this exact diagram, that gives you another way to check your solutions. If your solution ends up being the average of the two weights, you know something went wrong, unless the weights, and by extension the masses, are identical. Hopefully this has been an enlightening problem. Now let's move on to another standard book problem. Let's see, is this one... we don't need it. Okay, what about you? Okay, this one has some trig in it. So it says a bag of cement. I'll start by drawing the drawing before I read out the problem. So it says we have a bag of cement hanging from 3 wires, and then they've drawn it so they've got something like this. And then I guess we have a ceiling or something. And they've got this angle is theta 1. This angle they called theta 2. And then over here they've got a bag of cement, and they just labeled it as having a weight of little w. Little w, or what I typically call Fg, force of gravity. So it says, a bag of cement hangs from 3 wires as shown in the figure. 2 of the wires make angles theta 1 and theta 2 respectively with the horizontal. It's got 2 parts. Part A show that if the system is in equilibrium, then Part A show that T1 equals W cosine theta 2 over sine of theta 1 plus theta 2. Those of you who have not had pre-calculus and trigonometry, you're not going to be able to solve this. And thankfully, they don't tend to ask you questions that require using this trig identity that we're going to use in this problem on the AP exam. So don't worry too much if you don't know what I'm about to use to solve this, but for those of you who do know the trigonometry behind this that I'm about to use, I think you're going to find this problem to be rather interesting. So yeah, show that if the system is in equilibrium, then this is true. So show that if system is in equilibrium, and then part B, given that W is 325 newtons and theta 1 is 10 degrees and theta 2 is 25 degrees, find the tensions T1, T2, and T3 in the wires. And I guess they would have to mean this is T1, it would be associated with theta 1, this is T2, and then T3 and the reaction to it on the knot would be there. And I guess the reactions to T1 and T2 would be down here and down that way on the ceiling, but we're not going to concern ourselves with that. So part B I'm going to skip because it's really just plugging numbers into the formula. Part B, plug in numbers. The good news is if you get something like this on the AP exam, maybe not this one specifically because again, that trig identity, I don't think they expect you to remember it off the top of your head. But if they gave you something where they said, prove a formula, and then the second part is if the values of the variables are so on and so forth, calculate whatever. Even if you don't know how to prove the formula, you could still do part B. You could just use the formula they gave you, plug in the numbers and get the result and score some points. So in case I haven't said that before, there you go, now you have heard it. And if I have said it before, then now you've heard it again. If you don't know how to derive the formula, but you can still use it in other parts of your free response question, then go ahead and do it. Pick up the easy points. Anyway, I will be skipping part B because we all know how to plug numbers into our calculator. Part A is the more interesting part. So, color. What do I want to use? Let's use orange. Okay, T1 or FT1 is how I would normally call it, but I will go with their notation for now. And T2 and T3. They said the system is in equilibrium, so let's go ahead and write our equilibrium equations. We know if the system is in equilibrium, then the net force everywhere has to be 0, so the net force on this bag needs to be 0, which means T3 upward minus W downward has to be 0, so T3 minus W has to be 0, therefore T3 must be equal to W. Okay, and then we can basically cut off the bag of cement, and now we have T3 equal to W over here, and now we can do equilibrium on this node, this knot. So we're going to have net force Y on the knot is going to be forces upward. Let's see. If that is theta 1 over there, then if I were to draw a horizontal line over there, then this angle over here would also be theta 1, which would mean T1 sine of theta 1 would be the vertical component, while T1 cosine is horizontal to the left. Similarly for T2, T2 sine of theta 2 is going to be the upward component, while cosine gives you the rightward. So upward components T1 sine theta 1 plus T2 sine theta 2 minus downward forces is T3, which is just equal to W. Okay, and that's supposed to be equal to, of course, 0. Normally I write the 0 first, but you can still save it if you forget to do that. There's no reason that the 0 has to be on one side or the other, as long as it's part of the equality somewhere. Doesn't matter which side. T1 cosine theta 1 is to the left, so let's actually do right minus left. T2 cosine theta 2 minus T1 cosine theta 1 equals 0, which I guess leads us to the conclusion that T1 cosine theta 1 equals T2 cosine theta 2. Okay, so they want us to find an expression for T1, so let's try and solve for T1. I think what I want to do is take this second equation, add T1 cosine theta 1 to the right, and then divide by cosine theta 1. Actually, wait, no. I want to solve for T2, actually. So divide by cosine theta 2. Add T1 cosine theta 1 to the right, and then divide the cosine theta 2 over. So we get T2 is left alone, and we get T1 cosine theta 1 got moved to the right, and then we divided the cosine theta 2. And the reason I changed my mind there is, one, because we're trying to solve for T1, so if we're going to use substitution, we want to substitute the other variable that we want to get rid of. But also, because I wanted to have that loose cosine theta 2, I see it in the statement I'm trying to prove, so I probably want that to stay around. Okay. Plug this in for the value of T2 over there, and let's start that on a new page. Let's see, T1 sine plus T2 sine minus W. So T1 sine theta 1 plus T2 sine theta 2. T2 being this, T1 cosine over cosine. T1 cosine theta 1 over cosine theta 2. So that's replacing T2, and then sine theta 2. T1 sine theta 1 plus T2 sine theta 2 minus W equals 0. Minus W equals 0. Okay, I can add the W over to the right. So we get, and factor out T1, so T1, and then sine theta 1 plus cosine theta 1 over cosine of theta 2 sine theta 2 equals W. And where do we want to go from here? So we are trying to solve for T1. T1 equals W cosine theta 2 over sine of theta 1 plus theta 2. So I want to get W and cosine theta 2 in the numerator. Well, I've got my W, so now I need my cosine theta 2. So let's go ahead and multiply cosine theta 2. Multiply everything by cosine theta 2, and that gives me T1 sine theta 1 cosine theta 2 plus cosine theta 1 sine of theta 2 equals W cosine theta 2. If you are confused by what I just did there, I multiplied cosine theta 2 on the right hand side, of course, and on the left hand side I multiplied by cosine theta 2, which I distributed. So sine theta 1 got a cosine theta 2, and then over here, since there was already a cosine theta 2 in the denominator, that just canceled out. Okay, sine, cosine, cosine, sine. You might remember this as one of the sum and difference trig identities. You might remember this formula from pre-calculus trigonometry: sine of A plus B is equal to sine, cosine, cosine, sine, sine, cosine, cosine, sine, AB, AB, and then with sine, if there's a plus in there, then there should be a plus out here. And for those who haven't seen these before, we'll write the other three identities. Might as well. Sine of A minus B is also going to follow the sine, cosine, cosine, sine pattern. AB, AB. Cosine, whoops, cosine, not casine, cosine, casine. Cosine of A plus B. So for cosine, the pattern is cosine, cosine, sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine, sine. AB, AB. It's always AB, AB. And then cosine, when you have a plus in the parentheses, cosine will actually do the opposite. So it's going to have a minus in between those two terms. And then cosine of A minus B is the same thing, but switch the sign in the middle. The SIGN sign. Cosine of A minus B is cosine, cosine, sine, sine. AB, AB. And then since there's a minus over here, then we should have a plus over here. Cosine gives you the opposite. But yeah, the one we are using today is this very first one. And as for the derivation of these, well, once you derive one of them, you can just use the one that you do derive to figure out the rest, because you can take advantage of the fact that sine of a minus b, for example, if you know sine of a plus b, then you can write this as sine of a plus negative b, and then take this formula and replace cosine b with cosine negative b and sine of b with sine negative b, and take advantage of the fact that the sine of a negative is the negative of a sine, while the cosine of a negative is the cosine of the positive, and other things like that. Going from sine to cosine, you would just take advantage of the you would take advantage of the fact that sine of an angle is equal to cosine of 90 degrees minus that angle. And yeah, if you just take advantage of some of those simpler trig identities, then you'd be able to derive 3 of these after getting any one of them using the more complicated proof requiring geometry and stuff. But that's for your pre-calculus trig course. We're not doing that today. You can probably look up the proof in your pre-calc textbook. Anyway, sine A cosine B plus cosine A sine B, sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. Your A is theta 1, your B is theta 2. This is sine of A plus B. This is sine of theta 1 plus theta 2. So we have T1, and then this whole thing simplifies to sine of theta 1 plus theta 2 equals W cosine theta 2, and the last step is divide this over, and so we get T1 equals W cosine theta 2 over sine of theta 1 plus theta 2. Now, one thing you could do to give yourself a bonus question here is derive a similar expression for T2. That is a bonus exercise you can give yourself. But there we go. We've done the interesting part of that problem. So, yeah, trig identities might still have their uses in physics beyond just the Pythagorean identities. Okay, and that was the last problem I wanted out of this book. There was at least one problem I can think of that I wanted from this other book. Let me see if I can find it. And then if I can think of something else, we can do that. Otherwise, I might actually just call it a day early and end in 2 hours instead of the usual 3. We will see. Where is that question? I'm gonna have to look for it. It doesn't have a diagram that goes with it, unfortunately. And this book has multiple chapters involving force problems is the other thing. Oh, I think I found it. Yep, found it. Okay. So, it says, an 11-kilogram monkey is climbing a massless rope attached to a 15-kilogram log over a frictionless tree limb. The fact that the rope is massless, that's another assumption that we make. If you take the mass of the rope into consideration, you need to do calculus and stuff because it technically does have an effect on acceleration and whatnot, but it's telling you to ignore that, so we will. An 11-kilogram monkey is climbing a massless rope attached to a 15-kilogram log over a frictionless tree limb. This tree limb is essentially being treated as a pulley, sort of, as a light frictionless pulley. Part A, with what minimum acceleration must the monkey climb up the rope so that it can raise the 15-kilogram log off the ground? If after the log has been raised off the ground, the monkey stops climbing and hangs onto the rope, what will now be, Part B, the monkey's acceleration, and Part C, the tension in the rope? So this is an interesting problem because one of the objects attached to one of the ends of this rope is actually moving relative to the rope, which isn't something that we've seen before. Usually the rope moves with the objects. The objects are stationary relative to the ropes. But not today, not this time. So 11 kilogram monkey, I'm just going to draw a block. 11 kilogram monkey. And then the tree limb is essentially just going to act as a pulley. So if you wanted to draw a pulley here, you could. I didn't draw this really well. Let's make it bigger. Yeah, something like that. I'll just color it in. That way it doesn't look hideous. So yeah, there's a tree limb. And then there's a 15-kilogram log tied to the other end. And I guess, was the log on the ground? Yeah, because it said after the log has been raised off the ground, so the log should be on the ground, which makes sense that this would be the starting position. Right, if it would make sense that you start with the heavier side already on the ground. So yeah, 11 kilogram monkey jumps up, grabs the rope, and then starts tugging on the rope. So if the monkey is hanging from the rope, the amount of tension the rope has to supply to keep him hanging is different from the amount of tension that the rope is going to have in order to support the monkey pulling itself up on the rope. Remember, tension doesn't have a formula. Tension has just a maximum that can be reached for the given rope, cable, chain, whatever. And as long as it's under that maximum, the tension will just transform into whatever value it needs to be in order to fulfill the situation that it finds itself in. With the monkey acting on the rope, the tension has to increase beyond just the base amount necessary to support the monkey's weight. So yeah, with what minimum acceleration must the monkey climb up the rope so that it can raise the 15-kilogram log off the ground? What is the minimum acceleration needed? So that's part A. What is the minimum necessary acceleration for the log to just begin to lift off of the ground? That tells us how much tension force we need. That actually tells us how much tension force we need in order to just begin lifting the log. The log has force of gravity acting on it, 15G. And there needs to be a force of tension in the rope. For it to just begin to lift off, it needs to be 15G plus 0.0000 a million more zeros and then a 1. As long as it's a fraction of a fraction of a fraction of a fraction of a Newton more than 15G, the log will begin to lift up. So of course we're just going to say one force of tension essentially equals 15G. So we're going to say just lifting off the ground means force of tension is just a little bit more than 15G. We'll say equal to 15G because the difference is going to be negligible. Okay, so if the force of tension is 15G, then this monkey is going to have 11G acting down on it and whatever force of tension in the rope acting up on it. So if the tension in the rope has to be 15G, 15G minus 11G, net force on the monkey, in this case, net force monkey has to equal the mass of the monkey, 11 kilograms, times the acceleration has to equal the force of tension minus 11G. So in this specific case, 11 times A minimum has to equal 15G minus 11G. 15 minus 11 is 4G, and then 4G over 11. A minimum equals 4G over 11. Pretty easy. The only thing that's difficult about this is breaking out of that mindset that tension can be no more than what's necessary to support an object's weight. That is not true. That's just something that that's just an impression you get from doing too many problems where that is the case and not seeing enough problems where it's not the case. So yeah, let go of that sort of mindset because it is a false one. It's usually true, but that doesn't mean it's always true. Okay, and then we can plug in the numbers and might as well do it. It should be quick. 4 times 9.8 is 39.2. Divided by 11 is 3.5636. I'm going to round it to 3.564. Approximately 3.564 meters per second squared. All right, there we go. And then part B, if after the log has been raised off the ground, the monkey stops climbing and simply hangs onto the rope. Now we just have this standard problem. So basically the same drawing, but what we would change is, I guess if I had to redraw it, what would change is the monkey has climbed up, has pulled some rope out, and so some rope will be just kind of already down there, and then the monkey will be up here somewhere. And then the log will be up here. The log. I was about to say the limb, but just remembered the limb is up here, the log is down there, and then the ground is over there. Yeah, so now you've got this situation, which I guess if we remove this, if we just erase the section of rope that's just hanging loosely down there on the monkey's side, this is essentially just your standard pulley problem where you have a light object and a heavier object and the system is released from rest. And they ask you what is the acceleration of this system, right? If after the log has been raised off the ground, the monkey stops climbing and hangs onto the rope, what will now be the monkey's acceleration and the tension in the rope? Yeah, just standard problem from here. So What will the acceleration be? Well, now we can write net force log is equal to 15 kilograms times the acceleration of the system equals forces down, so 15g, minus forces up would be the tension force. And for this, I'm going to say clockwise is the positive direction, of course. And if I add this equation to this equation, what do I get from putting this together with this? 11a plus 15a is going to be 26a. And then force of tension minus 11g plus 15g minus force of tension. Tension cancels out. And we're left with 15g minus 11g is 4g. So we've got 26a equals 4g. Wait a minute. Isn't that what we should have done in the previous part? No. In the previous part, we only used mass of the monkey times acceleration because the accelerations were different. The log was going to have an acceleration of basically 0, while the monkey has the acceleration we calculated. But in this next part, parts B and C, the log and monkey finally accelerate as a system, so that's why. That explains the difference between the two problems. 4g being equal to ma of the monkey versus 4g being equal to ma of the system between parts A and B. Okay, divide by 26, so 4g over 26. Of course, we expect it to be less than 3.564, so look out for that. So 4g, 39.2 divided by 26 is 1.5076. I'm going to round to 1.508. Acceleration is equal to 1.508 meters per second squared. And I guess I should call this a system, but details. Okay, and part C, what is the tension in the rope? We've done this a million times before. Let's use this first one. So for part C, 11A equals force of tension minus 11G. Add 11G to both sides. 11 times A plus G equals the tension force. So 11 times parentheses 1.508 plus 9.8 is 124.388. I'm going to round that to 124.39. Force of tension equals 124.39 newtons. And there we go. Let me think. Were there any other interesting problems I wanted to cover before calling it a day? I mean, I'm sure there's more, but nothing coming to mind off the top of my head. I mean, this isn't the last we will see of force. Force is going to show up, in fact, immediately in the very next chapter. Force is related to energy. If you can't draw a correct force diagram, you're going to have trouble calculating energy. Although I guess it depends on which types of energy problems we're talking about. So it's not like we're going to stop seeing force. Force is still going to be in this course for pretty much the rest of the course. Let's see, it's involved in energy, it's involved in momentum and collisions, it's involved in rotational dynamics and uniform circular motion and gravitation, it's involved in simple harmonic motion, and it's involved in fluid mechanics for those of you in Physics 1. So, yeah, we are not saying goodbye to force, not by a long shot. Oh, right, here's a classic. Here is a classic. And we will wrap up with this one. So, last problem. Pretty simple description for this problem. Well, I have a version of it in the book that's a little bit more complicated in its description, but the same math is required either way. So let's actually do the one in the book. So it says a house is built on the top of a hill with a 42-degree slope, and they have a drawing of it. They have this hill, and then over there they have a house. I don't think the house is super important here as a detail, but there's a front door and some windows. And it says it's on a 42-degree slope. So this angle over here is 42 degrees. Subsequent slumping of material on the slope surface indicates that the slope gradient should be reduced. If the coefficient of friction of soil on soil is 0.55, and this is a coefficient of static friction, mu static maximum equals 0.55, through what additional angle phi should the slope surface be regraded? So in their drawing, they're saying that this slope is too steep and there's like rock slides going on. There's, well, maybe not rock slides, but they called it slumping of material on the slope. So they're saying the slope is too steep and it's a hazard, and they want to dig a little bit and flatten it out somewhat. So they want it to, basically, they want to cut it off to something like this. And in their drawing, the house is a little bit further to the right. Obviously, you don't want to dig under the house. That just means the house is going to topple over. But there's a little bit of space to the side of the house where they can dig up some dirt and lower this angle. So they want to reduce the angle by this much, and they called this amount phi, Greek letter phi. By how many degrees do you want to reduce this so that there's no longer a risk of slippage and rock slides and whatnot? Given that the coefficient of static friction for soil on soil is 0.55. So essentially what you want, the way to visualize this, because people might get confused since we're talking about movement of the soil, think of the soil as a really, really tiny block on the surface of this slope with some mass, m, whatever that mass may be. and it's going to be at some angle theta. And we want each and every one of these, I guess, particles of soil to have a net force of 0 on it, right? We want to make sure that the friction is enough to keep the soil from rolling downhill and causing landslides. So we want the net force to be 0, and I guess we can draw our diagram first. So there's going to be a force of gravity straight down. I will break it into components. So force of gravity cosine theta over here, and force of gravity sine theta over there. And then there's going to be a normal force acting on this thing, and there should be a static friction force of friction static, that prevents this soil from moving, that prevents this block, particle, whatever you want to call it, of soil from sliding down. We need to figure out at what angle that happens. So if we go ahead and set net force perpendicular equal to 0 and net force parallel to the slope equal to 0, let's see what we can find. Net force perpendicular equals 0. Well, that just tells us that normal force minus mg cosine theta is equal to 0. Whoops, did I write an equal sign there? Minus mg cosine theta is equal to 0, which implies that normal force is equal to mg cosine theta. Okay, done. Then we have net force parallel needs to be 0. So I'm going to say up the slope is positive. So we're going to say force of friction static, specifically when it's maxed out, is what we're looking for. Force friction static maximum minus mg sine theta has to equal 0. So mg sine theta has to equal force of friction static max. So I guess we'll write that over here. Force friction static max, which is mu static max times normal force, has to equal mg sine theta. And we already said normal force has to equal mg cosine theta. And would you look at that, the mg cancels out, so the mass doesn't matter. And it also doesn't matter what planet you're on. And if I divide cosine theta on both sides, sine theta divided by cosine theta, mu static maximum equals sine theta over cosine theta, which is equal to tan of theta. So if we're solving for theta, that means that the requirement is that the slope has to be equal to inverse tangent of mu static maximum, but I don't have enough space to write the max there, so we'll just call it mu static. So yeah, at what angle does the slope need to be in order to be flat enough to not cause a landslide? Let's go ahead and take the inverse tangent of 0.55. And that gives me 28.8, and I am in degree mode, so yeah, 28.8 degrees. Theta needs to be 28.8 degrees. Anything greater than that is too steep. So 42 minus phi has to equal 28.8. In other words, 42 minus 28.8 is equal to phi. So we need to shave off phi equals 13.2 degrees. We need to shrink this angle by 13.2 degrees for safety reasons. Yeah, there you go. The more classic version of this problem would just be this diagram right here. They'll give you a block of mass whatever. As you saw, the mass doesn't matter. And they'll tell you, what coefficient of friction is necessary on a slope of theta degrees in order for this object to not slip. Or they can ask the opposite. They can give you the coefficient of static friction and ask you, what angle do you need to stay under in order to prevent the thing from slipping? It could ask you the question in either direction, but the diagram and the relationship between the tangent of the angle and the static friction maximum coefficient is going to be the same either way. So yeah, don't be too surprised if you see that. I would not advise that you memorize mu static equals tan theta, because that's just taking away the wrong idea from this. Just don't be surprised if you see it in these scenarios where an object is meant to be in equilibrium on a simple incline with no other forces outside of the usual suspects acting on it. If we threw an applied force or a tension force or something over here, then all bets are off and this relationship ceases to be true. Although we will see something kind of like this when we get to circular motion. So try to remember this for that. We are going to see some interesting relationships, not involving tan of theta specifically, but involving the coefficient of friction and relating it to trig functions. Let's just put it that way. And I think that was the last thing that I wanted to make sure to get out of the way. I think with that we have covered a good number of problems now, to where if you studied them carefully and you also asked yourself, those bonus questions that I keep telling you to ask yourself every time you do a problem, see if you can ask yourself something more. See if you can figure out something that the problem didn't ask for, but that you do have the information to find. See if you can discover anything else in the problem. As long as you've been doing that, then I think you should be in good shape for force. So next time we are going to start the topic of energy, and compared to force, we are probably going to blitz through it rather quickly. There are some conceptual items of interest that we're going to have to cover with some more care, but it's not going to take anywhere near as long as we took with force. Energy is a chapter where if we've mastered force, it goes by rather quickly. And actually, same thing for the chapter after it, which is going to be momentum. So yeah, let's take a quick look at the course plan. Here we are, and in case this is your first time here, the course plan is linked in the description. This is just my overall plan for both Physics 1 and Physics C. I know it says Physics 1 course plan, but Physics C is going to be the same topics, except they're not going to do fluid mechanics. And once we get to that point, we're going to branch off, and I'm not sure what I'm going to do. Am I going to do two separate streams, one for each, or am I just going to do one stream and split it in half and dismiss one group of students? Or I'll have to think about that some more. But yeah, once we finish Unit 8 for Physics 1 students, we're going to continue with fluid mechanics. For Physics C students, we're going to go back and redo everything but with calculus inserted. And then for both, we're going to look at some other review items. But anyway, work, energy, and power is our next chapter, unit, whatever you want to call it. So, what do we want to do? Well, I guess what I would recommend is just reading some sections and definitely starting with this energy playlist from Flipping Physics. All of the videos titled Introduction to Blank you would probably want to watch. Let me think. Plan for next time is going to be introducing the basic concept of work, defining energy, and we're probably also going to discuss the concept of kinetic energy and the work energy theorem. I don't think we're going to be doing conservation of energy just yet, so you might want to hold off on that, because I don't think I'm doing that next time. That'll be after next time, in all likelihood. You might want to look at the work basics, and also this second one, kinetic energy and the work energy theorem. We might reach this far next time, but we'll see. And yeah, this third video, that's not next time. I highly doubt we'll get that far. That'll be for the stream after next. And if I look at the chapter 7 sections, 7.1 through 7.7, so chapter 7, let's see. So it looks like 7.1 and 7.2. If you like to read in the textbook, 7.1 and 7.2 will prepare you for what we're going to cover next time. And I guess you can also go up to 7.2 in the questions and exercises if you want. If you're bored over winter break and you want something to do, this would be my suggestion. And I think that is where we will stop for the day. So yeah, if you have questions, comments, whatever, that's what the comment section and the chat are for. If you ask in the chat and it's a really complicated question, then you might have to wait to get an answer, so be proactive and ask in the comments instead before the next stream. Although I'll probably end up answering it either way. Because, I mean, I've been tutoring for years and I kind of know all of the common questions by this point, or at least most of them. So I probably already have it built into my lessons that I'm going to be answering those common questions anyway, but it doesn't hurt to ask. And I lost my train of thought. What was it? I felt like I had one more thing to say before ending the stream. What was it? Oh well, it'll come back to me later. Anyway, enjoy your winter break, and for those of you utilizing it to study, keep at it and review what needs reviewing. If you need to rewatch old videos and stuff, kinematics is going to continue being a part of the course as well. There's going to be some kinematics in the energy chapter, so if that needs review and you haven't been reviewing it for this current force chapter, well, now you really, really need to review it. So yeah, look at that and any other previous streams that you feel like you could use a refresher on. And I think that's all my advice. Take care, enjoy more of your winter break, and I'll see you whenever next time may be. Class dismissed.